Hello and welcome back. During this video, I want to talk about the implementation of sparse modeling. In other words, how do we compute the alpha that we have seen in the previous videos? During the video, we are also going to discuss some theoretical results. I'm just going to mention their existence and why they are so important. Let's start with that. Assume that we have just produced a signal, x, as this product, basically as a sparse model. So assume that we know a dictionary D and we randomly pick an alpha with a few non-zero coefficients and we generate x. And now our goal is to find back this alpha. So now we know the dictionary and we know the signal and we want to compute its sparse representation. That's our goal right now. As we say later on, we're going to discuss about how to compute the dictionary itself. So, as we have seen in the previous video, we want to compute the alpha that has the smallest possible number of non-zero coefficients. That's also called the support. And we assume that there is no noise right now. We have just generated this signal. So it's kind of the ideal scenario. So that's our goal right now. And there are a number of questions. One of the questions is, why would we get, with whatever algorithm that we produce here, that we are going to explain in the next few slides, why are we expected to get exactly the same alpha that produced the signal? In other words, is that alpha unique? Can you think about a scenario where we know that alpha not necessarily has to be unique? And can you think of a scenario where we know that alpha will be unique? Let's think for a second about that problem. One example where alpha is not unique, if, for example, several of the columns of D are identical. So let's assume that this was generated by one of those columns. I can actually pick any other column because they're identical, and I can replace that alpha but by the alpha corresponding to that column. Assume that column 1 or 2 are identical. Assume that basically I generated this signal with exactly this pattern. So I generated it with the second column. But when I go to reconstruct, I can pick column 1 instead of column 2, and therefore I get a different alpha. So that's an example where basically the solution is not unique. An example where the solution is unique is in DCT, discrete cosine transform, or in the Fourier transform. We know that actually the transform of a signal in Fourier or in discrete cosine transform is unique. So those are cases. Now, what was the difference? In one of the scenarios, D was basically had repetitions. In the other scenario, we know that Fourier and the cosine, every column is independent of the rest. They are orthogonal to the rest. So it looks like the structure of the dictionary D has a lot to do with the uniqueness of alpha. Here comes a second question. Will I get, because in the previous case, at least the support, the number of non-zero coefficients, meaning the size of the support was the same. Could I get basically maybe even a more sparse representation than the one that produced it? And once again, it's not hard to think about an example of that. Assume that basically you generated a signal with all these three, and this is x. Now assume that by chance that x was part of the dictionary D. Then when you're going to try to recover, your sparsity goes back to 1. So you went from 3 to 1. What's the problem there? Once again, one of the columns is basically a combination of the others. So if you produce a signal that has such combination, then you might be able to get it back with actually less coefficients. So these two problems, actually, the questions depend a lot on a number of things. The dictionary, meaning its size, k, and also its general structure. And the basic idea, as we have seen from this example, is that we want the dictionary D to have atoms, columns that are as uncorrelated as possible to guarantee that basically we have unique solutions and that basically we get back the sparsest signal that actually produced the signal. So depending on the sparsity level, basically depending on the number of non-zero coefficients and on some conditions on the dictionary, there is beautiful theoretical results out there that guarantee uniqueness and that guarantee that we get the basically smallest possible support when we do the type of reconstruction algorithms that I'm going to show next. So it's important for us to know the existence of these very important theoretical results in the background that support the type of techniques that we are developing and that support the use and the exploitation of sparse modeling. Our goal now, assuming those theoretical results, is actually to solve sparse modeling. So we want to find, now we are given a signal y. Remember, now it's not the ideal case anymore. X is going to be represented by this, so this is our x. We want to find the representation of x given the dictionary D such that we get the smallest possible support, meaning the smallest possible non-zero coefficients, and we don't get too far away from the observation. And that's our goal right now, to solve this problem. This is actually what's called a combinatorial problem, and it's NP hard. It's actually, you cannot solve this problem as I just posed it in basically in realistic time. Let's just explain why. We're gonna basically do the following, which is the only way to solve exactly this problem. We start with L equal 1, so we look for a signal that has sparsity 1. That's what we are going to do first. So we generate all the possible supports of that signal. Because L is equal 1, basically the support means only the first one is active, or only the second one is active, or only the third one is active, and so on. Now, how many possibilities we have? We have already seen that. We have L chosen out of K. In the case of L equal 1, we have basically K possibilities. When we are going to iterate this, because then we are going to do K equal 2, we have of the order of K squared possibilities. And as L increases, we're going to have more and more possibilities. But for now, we basically have all the possible supports. Now, with each one of those possible supports, we basically go and solve the fitting problem. So we say, okay, what happens if I'm only going to use the first atom? All what's left is to pick the scale. How much of that first atom will I use? And then I solve this problem. This is a least squares problem. It's a very simple quadratic problem. Many ways to solve it, but the basic idea is that we are going to project the signal into the atom that we have just selected. And we see, basically, we try for each one of those, and we actually see what's the error. If the error is less than what we want, then we're done. We basically pick the alpha that produced that small error. Now, if the error is not, then we increase the support. So we have just tried basically with L equal 1. Now let's try with L equal 2. So we pick all the possible supports that have two active, two non-zero coefficients. So we say, okay, how can I approximate the signal Y with the first and second atom together, or with the first and third atom together, or with the 7th and the 25th atom together? So we pick every possible two. Again, there are two chosen out of K, which is in the order of K squared, and we try all of them. We solve for each one of them this problem. Again, just a least squares problem or a projection onto the subspace generated by the selected atoms. We try again, and we keep going, and we keep going. So that will solve this. Basically, absolutely no problem. What's the problem with this technique? The problem with this technique is the following. Assume that k is equal to 1000. That's a standard size. It's a good size. As I say, it's about the size that we're going to be using when we talk about image denoising. And assume that I tell you they have to pick 10 atoms. So basically it's 10 chosen out of 1000. That's about of the order starts being the order of possibilities starts being about the order of 1000 to the 10th, something like that. So it's a very, very large number. Assume that each one of the computations that we have here takes about 1 nanosecond. So you try all possible supports of size 10, you solve this problem in 1 nanosecond. These are all reasonable numbers. What you get is that you're going to need a long, long time to solve this problem. Look at this number. It's a huge number. That's how much you're going to need to solve the problem if I already gave you that L is equal 10. Imagine what will happen if you have to run over all possible L's. It's impossible. That's why the problem is NP hard. It's impossible to solve as it is. So, are we done with this week? We just presented a great model, but we cannot solve for it. No, of course we are not done. Now we are going to have to find a way to solve this. How do we do that? There is actually a couple of fundamental ways to solve this problem. Again, a good fitting with as sparse as possible representation. There are, again, two ways to do that. One way is what's called relaxation methods. Can we change this for something that is solvable? Something that we can actually do in our computer? Meaning, can we relax our condition in such a way that is almost the same, but we can solve it? The other way is to do what are called greedy algorithms. And that means, okay, forget about finding all of them at the same time. Give me the most important atom, then the second, then the third, and so on. So let us basically briefly present both of these techniques. Relaxation methods are also sometimes called basis pursuit methods. This is our problem. This is what we want to solve. Relaxation methods will change this. Look what I'm doing. I'm replacing the zero norm or pseudo norm by the one norm. I'm now not just counting the number of non-zero coefficients, I'm basically counting with their magnitude. Remember, in the L0 norm, we had a penalty, which was something like this, flat. Okay, so there was no penalty when you're zero and the same penalty when you're non-zero. Here in the L1 norm, this was the type of penalty. It increases with the magnitude. Now we are a bit surprised. The beauty of this is that under certain conditions on D, under certain conditions on L, the level of sparsity, basically we can guarantee that these two are equivalent. This is a fantastic result. It says that I can move from an NP complete, unsolvable problem into an L1 problem. This is a convex problem. It's solvable and sometimes obtain exactly here the solution I was looking here, but in a reasonable time. Very beautiful theory behind this. And it's not the only case, but it's a powerful case where relaxation, actually, we don't lose anything by doing relaxation. And this problem has been studied quite a lot. As I say, it's called the basis pursuit. It's convex, So we can solve, there is a lot of algorithms in the literature to solve it. And in the packages I mentioned that are free for you to download and to play with sparse modeling, you have implementations and very efficient implementations of this. And this actually has been the source of a lot of research in the community, because now that we know that this is convex and is solving under certain conditions the original problem, let's try to solve it the best possible way. And this opened the door to a lot of excellent research in this area. And I'm just mentioning a few here. The literature is huge, and you might actually know about it from your own research area. Now, the second way, so this is the relaxation way, and as I say, extremely powerful. So you can pick to use one. The second one is the greedy approach. The greedy approach is often called the matching pursuit. And the idea is very, very simple. Again, remember, we have the signal that we're trying to approximate, that would be Y. We have our dictionary D, and we're trying to find the sparsest possible way to represent this signal. Now, what we do, and matching pursuit is a standard technique in the statistics community, and it was brought into signal processing about 20 years ago or so. The basic idea is, let's first find the most important atom in the dictionary. So you go and travel the dictionary. Let's observe what's happening here. You travel the dictionary and you find the first one. So once again, you go, you travel the dictionary, and you find the most important one. Why do I mean by the most important one? The one that minimizes the d alpha minus 1 square. So we have the d alpha minus y square. And this no, this is alpha, just was cut. This is no, this is no, y is no, this is d, this is y, and supports 1. So you try the first one, you try the second one, you try the third one, you try the fourth one, the one that does this the best. Actually, because this is the metric we're using, this one will be the one that maximizes the inner product with the signal y, basically, which is the one that is most parallel to the signal y. That's going to be this one. Now I keep it. I cannot give it back. In contrast with what we saw in the previous slide, that we basically try L equal 1, then try L equal 2, then try L equal 3. This I'm forced to keep. That's why the technique is called greedy. Once you select it, you keep it. So now I selected this, I keep it. I keep it, and there is still an error here. If the error is below what I wanted, I stop. If not, I have an error. Now the next step is pick the one that helps you to make that error the smallest possible. So for the first one was y, what we are trying to approximate. For the second one, we're trying to approximate the error. If we approximate the error, we add that atom to our collection, and we are starting to shrink the error. So the next time, you keep this one, and basically you go to the one that does the best fit to the error so far. So again, you try all of them, and you keep the one that minimizes the error. Let's just see that again. You try all of them, and you keep the one that minimizes the error. Now please note, I kept the first one, and I'm now keeping the second one. Okay, so I kept the first one and I kept the second one. Now I have a new error because I'm using two atoms. I have a new error, and I'm gonna pick the third one that basically approximates that error again. And every time, all what you're doing is inner products to approximate those errors. And now the algorithm is doable, because for every one that you have to try, you basically try n times. You're picking one at a time instead of picking this L at a time and interchanging and putting back and trying new ones. The one you pick, you stay with it. And now this algorithm is very efficient. It's just a bunch of inner products all the time. And you stop when you go to a reasonable error, an error that satisfies your requirements. Now, this is what basically I wrote here. You stop when your error is satisfied. There are some variations of this. The most important one is that every time that you pick a new atom, because it's the most important one, you take again your signal Y and you project into all the selected atoms. In other words, when I pick the first atom, I had a certain coefficient alpha here. When I pick the second atom, I got a certain coefficient. Now these two are already selected. So maybe I can take the signal and change the actual value here and the actual value here to get a better error. If I'm already selecting it, why to stay with the actual coefficient that I got when I selected it? I'm allowed to change it. So every time you change, you do a projection onto the subspace of all the selected atoms. Again, that's a least squares procedure, very fast to implement. So, orthogonal matching pursuit, you select the best atoms so far, you project onto the best selected atoms, that gives you an error so far. Next step, you select once again the best atom to minimize that error that you're getting so far. You project onto all the atoms and then you keep going. So that's a very simple algorithm. Again, it's implemented in some of the software that we give you the link for. So the basic idea is now we have techniques to solve this problem. We have techniques which are basically of several classes. The greedy algorithms that I just mentioned to you, that you go one at a time. There are variations of that. There are many, many variations. Some people say, why don't we pick two at a time? I do have some computational time to do that. And things like that, or the orthogonal matching pursuit that I mentioned. There are the relaxation algorithms. The literature is huge in that topic as well. And the basic idea was to relax this by something that will give us, hopefully, the same result we were looking for. And there are hybrid algorithms that do both of them at the same time in some very clever combinations. Now, why should they work? Because there is theory behind them that tells us that sometimes the relaxation, although it's a relaxation, it actually produces the right results. There are theories that gives us conditions for that. There is theory that gives us conditions for the greedy. Although it's greedy, sometimes it produces the right result. For example, if the matrix D is a Fourier matrix, you got the right results there. So there are ways of doing this kind of transform this basically L0 type of approach in completely solvable. And there is, again, beautiful theory that tells us when relaxation or greedy actually gives us the result we were looking for. If our problem, for example, the D matrix, doesn't hold those conditions, in practice, we still use one of these two classes of algorithms. Why? Because solving the real problem is not doable. It's impossible. So the best we can do is do either a relaxation or a greedy. And if we are in the right conditions, we get the exact solution we were looking for. If not, we hopefully get a very good approximation of that. So where are we so far? We started by image denoising and looking for the need of modeling. We derived sparse modeling as one way of doing a model of images that will help us in denoising. Now we discussed some of the problems, and basically we saw how to solve, how to compute the alpha that will give us the representation. The next step is the dictionary, and that's what we're going to do in the next video. Thank you very much. I'm looking forward to that.